So here's how the problem finished out from the first part of our lecture here today. Take the antiderivative to get these two expressions, plug in the endpoints, spend a lot of time cleaning up the arithmetic here, and you end up with pi over 3. So, okay, I guess I didn't expect a huge area. It's kind of cool that it's related to pi, but you know, the nice thing is you can check this with a graphing calculator, but it can't tell you that, gee, this was pi over 3. It's just going to give you a decimal value, like 1.04 something. So you can check it on your graphing calculator, but it's not going to exactly tell you the answer. Okay, we got to move on. So we're going to move on to section 6.2, which is volumes. So this is part one of two methods that we're going to work with, finding the volume of a solid of revolution. And let me see if I've got something that we can look at here. Yeah, this one's pretty good. So what we're going to do is take a figure, and that figure is going to actually a couple curves. That figure is going to carve off an area. And then we're going to rotate that area around an axis. And it could be anything. It doesn't have to be the x-axis or the y-axis. It could be around y equals -2 or x equals 6. It's a lot of possibilities. But this one's going to be rotated around the x-axis. So let's take a look at that as we do that. And as we do that, it's going to sweep out a stick or a shape that kind of looks like a candlestick as you rotate it around the axis. We're going to want to try and find the volume of that object. Now, there's a lot of objects in our world that are solids of revolution. I'm looking at my bike bottle up on my shelf, the rotors in your car, candlesticks. There's no end of things that are shapes that are solids of revolution. Well, we're going to calculate their volumes kind of in the same way that we did with, or we're going to use some of the same things we did with our area, is we're going to work with a slice. So let's start with an example. And let's do y equals the cube root of x, and y equals 2. And y equals 0, not y equals, how about y equals 0? And x equals 8. So those are going to be the three functions that bound my region. And I want to take a look at what those functions look like. And I also need to tell you, or the problem would need to tell you, what axis you're going to rotate around. So we're going to keep it simple with this first example. So we're going to rotate it around the x-axis. So rotate it around the x-axis. So let me draw this, see if we can't figure out some more things about it. So something like this, and something like this. Now I'm not exactly sure what the cube root function is going to look like, but it's going to look something like that. So y equals a cube root of x up to x equals 8. So, okay. If x equals 8, then that makes us the point 8 and 2. And of course, this is the x-axis, the line y equals 0. And we want to find what happens when we rotate this around the x-axis. And when we rotate that around the x-axis, it's going to sweep out a volume. It's kind of going to look like a sideways volcano, is what it would look like. A shield volcano, nice and smooth, or like a dome shape. And just like before, we're going to take one slice in that region because we don't have a geometric formula for this. And our trick in calculus is to start by building up these formulas through approximations. And so let's now just think about rotating that one slice around the x-axis. Now, what's going to happen to that slice? What kind of a figure is it going to trace out? Well, let me help you by letting you look at some of the illustrations in the book.
A disc.
Yeah, when you rotate that slice around the x-axis, you're going to get a disc. You're going to a disc shape. So basically, a short cylinder is what you've got. And then you can make an approximation by adding more disc, and then even more disc. And eventually, you're going to take the limit as the number of disc approaches infinity. And so what was an approximation in terms of an area times a width, which is going to be the volume of one such disc. When you add all those up and let n go to infinity, you'll end up with an integral. So this all does come back to integration. There shouldn't be a single problem on any of your tests that doesn't involve something from calculus. All right. So when I rotate it around the x-axis, I get a disk. And let's find the volume of one disk. Okay. So volume of one disk, it's really going to be the height and the area of a cylinder times the base of a cylinder times its height. So let me draw this. There's our little disk, like that. And let me remind you of the volume formula for a disk. So actually, I don't want to do it there. Keep it color coordinated. There we go. Volume of one disk is going to be the area of the base or the lid, which is going to be pi r squared, that's the area of a circle, times the thickness or the height. Now in this case, that's a dx. So times the height, or pi r squared times dx. So the next thing is, okay, what's r? R is going to be the radius. It's going to be the distance from this point here to your axis of rotation. In the vertical direction, when you want to calculate distance, it's going to be like it was in the last section, top minus bottom. So for us, that's going to be square root or cube root of x minus, well, 0. Because that's the height of the x-axis. So we'll just call that x to the 1/3 power. Let me take that x to the 1/3 power and plug it in for r and get a formula for the volume, pi times x to the 1/3 squared times dx. Or better yet, pi times x to the 2/3 dx. Cool. So now I want to integrate that. That's my integrand. So let's take a look at what we're going to do to integrate that. 0 to 8. I'll take the pi out in front, x to the 2/3, dx. Now I'll give you a choice here. Do you want to finish this one up with numerical integration, or do you want to do it all out? Doesn't matter to me. Okay, vote for do it out. Let's do it. So I need to find an antiderivative here. Probably not a bad idea to do a few of these out. If you add one to the exponent, we'll add 3/3 to 2/3, and I'll get 5/3. Divide by the same exponent, which is 5/3. And it might not be a bad idea to clean up that exponent a little bit, or that expression. So it's going to be pi 0 to 8 of 3/5 of x to the 5/3. So pi times 3/5 of 8 to the 5/3 minus, we'll just call it 0, right? Because when you put in 0, it's all going to be 0. That's going to be 32 times 3 is 96 pi over 5. Okay, not too bad. So kind of a gentle nudge into volumes here. How are we looking with that one? Let's try some more. What I might be doing is coming back at a couple of these examples and working them on different axes of rotation, just to show you what a difference that makes. And one thing I want to be clear about right now is that when you're doing the disc or washer method, which is coming up soon, for the disc or washer method, we haven't done one by washer method yet. Always. So the caps is my way of screaming this into your notes. Always take a slice perpendicular to the axis of rotation. So if you're rotating something around the x-axis, you're going to take a dx slice. If you're rotating something around the y-axis, it means you're going to take a dy slice. It always has to be perpendicular to your axis of rotation. That's huge. On your exam, sometimes I'll say, set it up by the washer method, set it up by the shell method. And the way you take your slice is literally like half of the points that I award for that problem. Because if you take the slice in the wrong direction, you're doing the wrong method. Okay. So back to my example here. Let's take a look at this example. Y equals 4, x equals 0, 2x equals y squared. And we're going to rotate this around line y equals 4. So that's kind of interesting. We'll see what happens when we do that. So let's say we're gonna have a curve that kind of looks like this. And line y equals 4 is gonna be horizontal. It's gonna be like this. You don't have to know what all these graphs look like. I mean, I hope that you know that the y-axis is the equation x equals 0. I hope you know what a horizontal line looks like, y equals 4. And then, of course, 2x equals y squared. Well, maybe you're not as keen on that one, but could be. You could solve for y here and get more of a familiar function, square root function. Of course, there's a plus or minus, but the minus would be below the x-axis. So we're not going to graph that one. We're just going to graph this one. So it's this region that we're going to work with. And I want to rotate that around the line y equals 4. So this line up here. And that much has to be given to you. You have to be told where you're going to rotate this around. Ashley, am I going to take a dx slice or dy slice here?
I believe that you would take a dx slice.
Good, because I have to take something perpendicular to my axis of rotation. So I have to take a vertical slice, and that's going to be dx slice. So good job. Thank you. All right, so dx slice here. X. And when I rotate around the x-axis, or the line y equals 4, then because this dx slice is flush with my axis of rotation, when I rotate this around, I'm going to sweep out the volume of one cylinder or one disk. So the volume of one disk. Well, it's going to be pi r squared times the thickness. But I got to be careful about my radius. What expression am I going to use there? So let's see if we can't figure out an expression for r. Because I'm taking a dx slice, r is going to be something in the form of top minus bottom. Can someone put in top minus bottom for me? Justin, you out there. What's our top function? Jackson C. Top minus bottom, what can I put in here, please?
This is going to be 4 minus the square root of 2x.
Perfect. 4 minus square root of 2x. So that's my r. It's just the top function minus the bottom function. So cool. Let's figure out the volume then. I need to figure out what r squared is. Well, I don't really need to figure it out. I can just do pi times 4 minus square root of 2x squared dx. So cool. All right. Now I need to figure out my limits. Where am I going to integrate to and from? So I'll put the pi out in front here. I've got 4 minus 2x to the 1/2 squared dx. Well, what about my limits? I mean, on one end, I think it's probably pretty clear, but on the other end, it's not as clear. What's the lower end? Jenna, what's the farthest left that I can take a slice here, please?
Is it 0?
Yeah, 0. So that's my lower limit. Can someone suggest what my upper limit would be? And thanks, Jenna.
8.
8 seems pretty good. But if you're not sure, you can do a couple things. You can put it on your graphing calculator, try and find the point of intersection. You can put it on decimals and try and find the point of intersection. If you're really desperate, we could actually do it by hand. It'd just be, where does 4 equal the square root of 2x? Square both sides, it'd be 16 equals 2x. So 8 for x. So that's what we wanted right there. 8 for x. Now it's the setup that's important in these things, and getting this setup is where I want us to go. Are we okay with how we set that up? All right, let's finish it off with our calculators. So let me cut over to here. And there's going to be some problems on the test where I say just set it up and finish with your calculator, and that's fine. If I ask you to actually do it all the way out, well, I'm sorry, you got to do it all the way out. All right, which means I want to see you putting in the upper and lower limits and that kind of stuff. But, you know, I'm not always a fan of that. I do throw a couple on there that you should be able to do. Now, when you're doing this expression, I need another set of parentheses. I need parenthesis 4 minus square root of 2x. And then I have to exit here, so you press a right arrow, then another parenthesis, and then the square key. So I guess it takes a little bit of finesse to even do this on your graphing calculator. Well, let's see what we get. Now, this is probably supposed to be 21.33333333, et cetera, right? But I'm not getting that exact value. In fact, if I try to do the math answer to fraction stuff like I did just a little bit ago, it's not going to give me anything. So, okay, it's good to verify it, but it kind of looks like 21 1/3. So I think that would be 64 divided by 3. Let's just check it out. 64 divided by 3. There you go. Cool. So 64 over 3 times pi would be our final answer. Okay. Looking good there, I hope. But if there's something that I went over a little too fast and you're unsure of, let me know. I'll be happy to answer any concerns that you may have. Get your money's worth. Ask a question. Okay.
Hey, Jeff.
Yeah.
That message or that note, that special note you just wrote above about the rotation, perpendicular rotation. Can you see it? I'm sorry. Just take a quick picture of it.
Oh, okay, sure. So after class, what I do is I scan in the notes,
Gotcha.
and I'll post those on D2L. So if you do miss something, or heaven forbid, you miss the lecture altogether, then, you know, at least catch things in other ways. But
I'm
not a problem.
I joined in a little bit late.
Yeah, I noticed. In fact, I did a shout out for Nash because I had you last winter, I think.
Yeah.
Waited a long time. It was kind of funny. I mean, I literally in March of this year, I started getting emails about the class in July. So it's kind of cool for me to actually finally virtually meet you guys, because a few of you have been corresponding with me for a while now. All right. Let's do that one again with a little bit of a twist. So let me draw our function. And I'm starting not to like this writing instrument here. All right. And here, So I still have the same functions. It's going to be y equals a cube root of x. No, excuse me, not y equals cube root of x. Thinking of a different one. 2x equals y squared. Let's just clean this up a little bit. There we go. Y squared equals 2x. X equals 0. Y equals 4. Except this time we're going to rotate around the x-axis. And that's going to make a big difference. Let's see if we can't figure out what difference that's going to make. So let me give this a little bit of color here. And we're going to rotate this one around the x-axis. Line y equals 0. This is still y equals 4. This is y equals the square root of 2x. But there's something different about this one. First things first, Carl, what kind of a slice am I going to take? A dx slice or a dy slice?
I believe a dy.
Is dy perpendicular to our axis of rotation?
Oh, I guess not.
Not. So it's going to be a dx slice, right? So let's take a dx slice. It's going to be like this. And there's something different. When I rotate this around, the x-axis, I'm not going to get a disc anymore. Can you use your imagination to figure out what kind of a shape I am going to get?
Washer.
Yeah, a washer. So what's happening is shown right here. Because our curve, I'm not sure how well you can see this dotted line here, but that's going to be part of our curve. Because that doesn't touch the axis of rotation, because there's a gap, you're going to leave a hole when you rotate your slice around the x-axis. And that slice is going to give you a washer shape as opposed to a disc. So I want to find the volume of one washer. Now,
I have a question.
the short version of the volume of one washer is that really you're going to take and look at two things. In fact, let me draw the washer real quick. So here and here. And let's give it a little thickness.
Jeff?
Yes.
Jeff, I think Marco have a question.
Oh, yes.
Right. So if that's coming in contact with the x-axis, why is a hole getting made? Why isn't it all like?
Well, it only touches the x-axis right here. But if you take a look at our general slice, when you rotate this around, there's a gap here, right?
Oh,
And that gap is what's going to rise to this hole. Now, it's true, like I said, at this point, yeah, there is no gap. But in general, there is. And that's why we got to draw a washer as opposed to a disc. Does that make sense, Marco?
yeah, it does. Thank you.
Okay. No, I appreciate the question. Thank you. All right, so let's see if we can't figure out the volume of this washer. So what we're actually going to do is calculate the volume of the outer cylinder and subtract off the volume of the inner cylinder. So it's going to look like this. Pi times R2 squared, the outer radius, times the height, What's that height? Anyone? I'll give you a hint. I kind of color coordinated these for a reason.
It's dx, right?
Yeah, thank you. It's dx. So pi r2 squared dx minus pi r1 squared dx. And you can clean that up. In general, it's going to be pi times the square of the outer radius minus the square of the inner radius, like that. The big thing to notice is that you've got a disk or a washer method, not a disk method. That's because there's a gap here. So I need to calculate R2, hello to all you Star Wars fans, and R1. Just like before, R2 is going to be top minus bottom. And it doesn't hurt to have a decent graph for yourself. Let's see if we can't label some things, try and figure out a radius. So let's take a look here. That's one. And here's the other one. Which one's the shorter one? R1 or R2? That's going to be your inner radius. That's the one that's closer to the axis of rotation. So that's R1. R2 is this one. That's going to be your outer radius. So let's see if we can't do both of those. Kevin, help me out with R2 and R1. What's top minus bottom in R2?
In R2, it would be the 4 minus the root 2x.
Actually, got to go all the way down to the axis of rotation. So 4 minus 0, right?
Oh, yeah, sorry.
That's all right. How about the second one? R1, what would that be?
And then that one would be the root 2x minus 0.
Good, perfect. And I'll just write that as 2x to the 1/2 for my convenience. Actually, it's not going to matter too much, but awesome. Thanks, Kevin. All right, so let's put both of those expressions in up here. That's going to be pi times 4 squared minus 2x to the 1/2 squared dx. Now that's going to simplify. Pi times 16 minus 2x dx. And that's not too bad. That's our expression for the volume of one washer. But I don't want the volume of just one washer. I got to add up the volume of all such washers. Now, when I grade your test, this is a major milestone. If you come up with this, that's great. If you come up with the right limits of integration, so let's take the pi out front, 16 minus 2x dx. What are the correct limits of integration? Where can the slice be taken and still be in the region? From what to what? Kamaya? Where could I take my slice?
0 to 8.
Yeah, good. So this would be 0 on the x-axis, and from our last problem, remember that was an 8. So 0 to 8. And let's finish this one off. Pi from 0 to 8, 16x minus x squared. 16 times 8 is 128 minus 8 squared gives us 64. Now, technically minus 0 for the lower limit, but 64, oh, pi. One thing you want to be careful about in WebAssign is whether or not they ask for the answer or if they ask for an approximate answer. Sometimes in WebAssign, they'll say, round your answer to 2 decimal places, in which case you type this into your calculator and you round it. But be careful that you round it accurately, because they can be kind of touchy on that. And it's something that bothers me, and I've written WebAssign about lots of concerns, but you do get 3 tries at these problems to get it right. And if you make a silly mistake, go back. They're going to give you new numbers, but the same degree of difficulty, same kind of problem. How's that one looking?
Is it possible that I just calculate the volume of the dome shape first and use the cylinder to minus that?
Can you describe that again for me, please?
Like last question, we calculate the volume of the dome shaped thing. And this rotation is like a cylinder. And then I minus the volume of the dome thing.
All right. So yeah, the outer volume. Okay. That's a brilliant observation. So what we've got here, when you rotate, if you rotated this whole area between 0 and 8 and 0 and 4 in the y direction, if you wrote that whole area around the x-axis, you're going to get a cylinder. And then you can subtract off the volume of like the inner part. So yeah, there's nothing wrong with that at all. That'd be pretty clever.
So like the both method is fine. Like I use in the exam is fine, right?
Sure. Yeah, that's a very clever way. I will look at your work, whatever you do. And as long as what you're doing makes sense, using techniques that we taught in class, that's cool. That's cool.
Okay,
And what you suggested is fine. It sounds really good. Okay. Let's do a couple more. Some of my students from last semester, did you guys like it when we drive the volume formula for a sphere? Was that a good problem?
Yeah.
Because we're used to it now.
Yeah, we're used to it now. All right, well, I'm not sure I feel a lot of love for the idea of doing it again. So let's do a slightly different problem then. Staying with these kind of regions, I want to rotate one around a different line, say x equal -3, and see what happens there. So last chance for any questions on this one. So if you're curious, last semester, one of the last problems we did was we took a circle and rotated it around the x-axis. Of course, when you rotate that circle around the x-axis, you're going to get a sphere. And so we calculated the volume of the sphere by, first of all, finding the volume of one cylinder. So it gave us something like this. Now what you had to do is you had to be careful that your limits went from -r to r. But when you plug that in, and here's the importance of having that dx here, for those of you who are in the habit of not writing it, that tells you what you're integrating with respect to. And since you're integrating with respect to x, then let's see, well, I think we use the even odd properties of our integral, but because you're integrating with respect to x, r squared just kind of stays the same. It's like a constant. It'd be like 7. When you integrate 7, you get 7x. This time you get rx squared minus the integral of that. You clean it all up, and you get 2 pi times 2/3 r, or altogether 4 pi r cubed over 3. So pretty cool calculation. If you guys are interested, I could scan that in along with the rest of the notes. But I want to do one. Let's take a region like this and rotate it around the line x equal -3. Let's see what happens there. All right. So our axis of rotation is x equal -3. Let's work with a slightly different function. Y equals, want to do a trig function? I don't see any takers. Probably should, but we'll get to some trig functions later on. So y equals, let's do the 4th root of x, just for giggles and variety. And this would be x equals 16 for our function here. All right. Ooh. Can someone tell me what mistake I've made? We're going to rotate this around line x equal -3.
You did.
Shouldn't your slice be the other way?
Yeah, good call. My slice should be the other way. I made a mistake. The slice has to be perpendicular to the x-axis. If it's not, you're doing a different method, a method that we're going to learn in section 6.3. But for now, let's just do it this way. So yeah, I'm just such in a habit of writing a dx slice. So my slice has to be perpendicular to the axis of rotation, so it's going to be a dy slice. There. Let's see here. Jackson F. Is this going to be a disc or washer method?
Washer.
Washer, good. Why?
To be honest with you, I'm not too sure off the top of my head. It just the pattern from before. Okay.
Well, let me try and make it a little more concrete here for you. It's going to be a washer method because there's a gap. My area here isn't completely flush with my axis of rotation. So if there's a gap between your area and your axis of rotation, then it's going to be a washer. So for instance, if I rotated this around the line x equals 0 or the x-axis, y equals 0, the x-axis, then that would be a disc method. If I rotated around the line x equals 16, again, that would be a disc method because my area would be completely flush there. But other axes of rotation are going to be a washer method because there's going to be that gap. So let's find the volume of one washer. So it's going to, that's going to be volume equals pi times R2 squared minus R1 squared times dy. It's important that we note that dy thickness. So I need a couple of expressions now for R2 and R1. R2, and R1. When you're taking a dy slice and you want this width, it's going to be right minus left. Right minus left. Right minus left. So I need 2 radii. Let me remind you of what this all kind of looks like. Let's draw ourselves a little washer here. You don't have to draw yourselves washers on the exam if you don't want to. That's fine. Just do it because I like to remind you of the geometry and what's going on. So we're going to have, whoops, I drew R2 twice, didn't I? Hate when that happens.
It's okay, just draw R3.
All right, so we just got to wish away that line. Let's do that. Use your telekinetic powers to scrub away that line. There we go. So here's going to be R1 is going to be your inner radius. R2 is going to be the outer radius. That's going to be your R2 right there. This distance right here is going to be R1. So let's carefully calculate both of these things. The easier one's going to be R2, of course. So let's knock that one off first. And at least get ourselves a couple nice easy points. So right minus left is going to be 16 minus -3, which is 19. How about the R1? Spencer, what's R1 going to be, please?
Well,
ooh,
something minus -3.
Yeah, there you go. Let me help out here. This has to be a function of y. We know that because of this here. So if I raise both sides to the 4th power up here, I get y to the 4th is my x coordinate. So it's y to the 4th minus -3. Yeah, I'm sorry. I didn't mean to set you up with a harder problem than I intended. So there you go. Y to the 4th plus 3. All right. I'll pause here. Are we comfortable with how we got these things? Okay. Let's set up our integration. It's going to be pi times R2 squared, so it's going to be 19 squared, minus R1 squared, which is going to be y to the 4th plus 3 squared dy. Ooh, this is going to get interesting. Again, it's helpful that we have this dy. It reminds you you're integrating with respect to y, and that your limits of integration should come from y. So, okay. What should my limits of integration be? Where can I go in the y direction? Find the limits of integration. Mahon?
Would it be 0 and then the intersection of 16 and this root of 4x? Or
Sure. And tell you what, how about if we put the 16 in here? What's the 4th root of 16?
2?
2, yeah. Perfect. So 0 to 2. Beautiful. How are we looking on that one? Let's finish this one up with our graphing calculator. So it's going to be 0 to 2. And thanks, Mom. 19 squared is what? 361 minus parentheses x to the fourth plus 3 squared. Now I'm typing it in with x's just because it's easy to get to the x on my calculator. You could type it in with y's, it's just not as convenient. So 608.7111, we might be able to get a nice fraction out of that. Yeah, beautiful. How about that? 27,392 divided by 45 times pi. Beautiful.
Would that be the correct answer on Robosign?
Yeah, the only time it wouldn't be the correct answer is if they ask for a decimal approximation. And be careful because a lot of times they'll say round it to this many digits. If you don't round it, it's like, oh, you kidding me? It's annoying. That's why I'm giving everyone a 4% bonus up front, no questions asked. In fact, there's a lot of people that finished last semester with over 100% on their homework. And that's a big boost in terms of your final grade.
Make it 8%.
So, question?
Make it 8%.
8%? I think 4% worked out pretty good. We'll see. We'll see. These are going to be challenging problems. There's no doubt about it. How are we looking there? Looking okay with that one?
Sorry, what if the rotation is x equal to 3? Is that the same?
No. I mean, that would be a big problem because x equals 3 would cut into your region. So, yeah, that'd be a much different problem. It'd be a much different problem.
We won't be something like that, right?
If I wanted x equals 3 for the axis rotation, I would stop your figure here. I would just put all of it to the right of it. I mean, the stuff to the left of it would actually be irrelevant anyways, because when you rotate it, that would be swallowed up. So yeah. I would give you a slightly different problem. Yeah.
Okay, thank you.
Yep, you're welcome. Cool, well, let's take a break here. A well-deserved one. So I'll see you again in 6 minutes.